In the freezing workshops of Aberdeen Proving Ground, Maryland, on the morning of December 7, 1942, a 38-year-old metallurgist named Dr. Harold Edmund Frost stood before a room of senior military officials and watched their faces turn from skepticism to outright mockery. He had just proposed treating armor-piercing shells with what he called a dual-stage tempering process, something his colleagues dismissed as metallurgical nonsense that violated every established principle of hardening steel. The officers believed they understood armor penetration perfectly well, that more velocity and heavier shells were the only answers to the German heavy tanks appearing in North Africa. They had no idea that within 18 months, Frost's supposedly idiotic idea would transform the balance of armored conflict on 3 continents, turning impenetrable steel monsters into vulnerable targets. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you are watching from. It really helps support the channel. This is the story of how one man's willingness to question fundamental assumptions about metallurgy, combined with desperate necessity and meticulous experimentation, created a breakthrough that military historians would later identify as one of the most significant, yet overlooked technical achievements of the entire conflict. It is a tale of transformation, where failure became innovation, where mockery turned to vindication, and where the seemingly invincible met an unexpected vulnerability born not from brute force but from understanding the hidden nature of hardened steel. Harold Frost had spent 17 years studying the crystalline structure of metals before the conflict began. He had published 23 papers on grain boundary mechanics and heat treatment cycles, work that most of his peers considered overly theoretical and disconnected from practical engineering. His university position at Carnegie Mellon had been comfortable but unremarkable, his reputation solid but unspectacular. When the United States entered the conflict in December 1941, Frost volunteered for the War Department's Metallurgy Research Division, hoping his expertise might prove useful. He arrived at Aberdeen in February 1942, assigned to a team investigating why American armor-piercing ammunition was performing so poorly against German armor plate. The problem was becoming catastrophic. By the autumn of 1942, intelligence reports from North Africa painted a disturbing picture. The new German heavy tanks, particularly the Tiger model that had begun appearing in Tunisia, were proving nearly invulnerable to standard Allied anti-tank weapons. The Tiger mounted armor plate, 50 to 100 millimeters thick on the front hull and turret, made from high-quality nickel-chromium steel that had been face-hardened through sophisticated heat treatment. American M61 armor-piercing shells, fired from the primary anti-tank weapon of the time, the 3-inch gun, were shattering against this armor without penetrating. British 17-pounder guns were having similar problems. Tank crews reported hitting Tigers multiple times at ranges under 1,000 meters and watching their shots bounce off or fragment uselessly. Lieutenant Colonel Marcus Webb, who commanded the Ordnance Department's Ammunition Research Section, had assembled a team of metallurgists and ballistics experts to solve the problem. Their initial approach followed conventional wisdom: make the shells harder, increase the velocity, use heavier projectiles. For 6 months they experimented with different steel compositions, adding tungsten and molybdenum, increasing carbon content, and refining quenching procedures to create the hardest possible projectile cores. The results were discouraging. The harder they made the shells, the more likely they were to shatter on impact rather than penetrate. It seemed they had reached a fundamental limit. Frost studied the problem differently. He requested samples of captured German armor plate and spent weeks examining the microstructure under powerful microscopes, mapping the grain patterns and measuring hardness variations at different depths. What he found fascinated him. The German armor had a specific hardness profile, extremely hard at the surface, gradually softening toward the interior. This was the result of their face-hardening process, which created a tough, ductile core beneath a wear-resistant surface layer. It was brilliant defensive metallurgy. But Frost began to wonder if it might also be a vulnerability. The conventional approach to armor-piercing ammunition called for making the shell as uniformly hard as possible throughout its entire cross-section. The theory was simple: Harder material could crack softer material. But Frost's research into grain boundary mechanics suggested something different. When an extremely hard projectile struck extremely hard armor, the impact created massive shock stresses that propagated through the crystalline structure of both materials. In a uniformly hard projectile, these stresses had nowhere to dissipate. They concentrated at grain boundaries and microscopic flaws, causing catastrophic fracturing. The shell essentially shattered itself. What if, Frost wondered, the projectile could be designed with a hardness gradient similar to the armor it was attacking? What if the nose could be hard enough to penetrate the face-hardened surface layer, but the core could be tough enough to absorb impact stresses without fracturing? It would require precise control over the heat treatment process, creating different metallurgical properties in different parts of the same piece of steel. This is what Frost proposed in his December presentation. He suggested a two-stage tempering process that would leave the tip of the shell extremely hard, but temper the core at a higher temperature to increase its toughness and ductility. The senior metallurgists in the room immediately objected. Dr. Raymond Holbrook, who had 25 years of experience in armor plate manufacturing, called it thermodynamic impossibility. You could not selectively heat-treat different parts of a solid steel projectile to different degrees, he insisted. The heat would conduct throughout the piece, homogenizing the treatment. Even if you could somehow manage it, you would create stress concentrations at the transition zones that would cause failure. Frost had anticipated these objections. He proposed a solution that seemed absurdly simple. Don't heat the entire projectile uniformly. Instead, use induction heating to selectively heat different zones to different temperatures, then quench in stages. Heat the tip to 1,100 degrees Celsius and quench it immediately for maximum hardness. Then reheat just the midsection to 650 degrees and quench. Finally, temper the entire shell at 450 degrees. The overlapping cycles would create smooth transitions between hard and tough zones. When Colonel Webb asked if this had ever been attempted, Frost admitted it had not. When asked if his calculations proved it would work, Frost acknowledged they were theoretical. When pressed on whether he had any physical evidence this approach would succeed, Frost said simply that he would need to run experiments. The meeting ended with Webb's grudging approval to produce a small batch of test shells using Frost's method, primarily because every other approach had failed. Frost spent the next 6 weeks in the proving grounds machine shops and heat treatment facilities. He worked 16-hour days, personally supervising every step of the production process. The induction heating proved extremely difficult to control. Too much heat conductivity, and the temperature gradients would equalize before quenching. Too little, and the transitions would be too sharp, creating the stress concentrations Holbrook had warned about. Frost went through 73 projectiles before he produced 12 that met his specifications. Microscopic examination and hardness testing confirmed he had achieved what his colleagues said was impossible: a projectile with a Rockwell C hardness of 62 at the tip, decreasing to 48 in the midsection, then back up to 54 at the base. The first live-fire test took place on January 28, 1943. The target was a section of captured German armor plate, 100 millimeters thick, mounted on a test frame at a range of 800 meters. A 3-inch anti-tank gun fired 6 conventional M61 shells first as a control. 3 shattered completely. 2 made shallow craters, but did not penetrate. 1 ricocheted. Then they loaded Frost's modified shells. The first shot struck the plate with a different sound, a sharper, cleaner crack. When the test crew inspected the target, they found a neat hole completely through the armor. The shell had penetrated and exited the backside, remaining largely intact. The second and third shots produced similar results. The fourth shot struck at a slight angle and still penetrated. The fifth and sixth shots were fired at 1,000 meters, a range at which conventional shells had no chance. Both penetrated. The test crew was stunned. Colonel Webb, who had observed from the firing line, walked to the target in silence, running his fingers over the entrance holes. The edges were clean, almost machined-looking, completely different from the spalling and fragmentation typical of shell impacts. The projectiles had behaved like solid punches, driving through the hardened face layer without shattering, then carrying their momentum through the softer core steel. Frost's theoretical framework had proven correct. The hard tip cracked the face-hardened layer, creating a path of least resistance. The tough core then followed through, absorbing the massive compression forces without failing. The hardness gradient matched the armor's hardness gradient, allowing the projectile to essentially flow through the steel rather than fighting it. It was metallurgical judo, using the enemy's own strength against them. Production authorization came through in February 1943. The Army Ordnance Department ordered immediate conversion of all armor-piercing shell production to the Frost process, as it was now being called. Manufacturing proved challenging. The induction heating required new equipment and training. Quality control was critical. Shells that did not meet the precise hardness specifications were rejected. Initial production rates were slow, just 500 rounds per day from the primary facility in Michigan. But by May, as workers gained experience and additional production lines came online, output had increased to 7,000 rounds daily. The first Frost process shells reached North Africa in April 1943, just as the Tunisia campaign was reaching its climax. They were distributed first to specialized tank destroyer units equipped with 3-inch guns. Captain Thomas Ridley, commanding a company of M10 tank destroyers attached to the 1st Armored Division, received his allotment of the new ammunition on April 18th. The shells came with special markings and brief technical notes explaining they were experimental and should be used against heavy armor targets only. Ridley's first opportunity came 4 days later during an engagement near Hill 609. His unit encountered 3 Tiger tanks supporting a German counterattack. Standard procedure against Tigers was to attempt flank shots, as frontal armor was considered impenetrable at normal combat ranges. But Ridley's lead destroyer was caught in the open with a clear frontal shot at approximately 900 meters. The gunner, Sergeant James Mitchell, loaded one of the new shells and fired. Through his periscope, Mitchell watched the Tiger lurch to a stop, smoke beginning to pour from hatches. The crew evacuated. Post-action inspection found the shell had punched completely through the front armor, penetrated the crew compartment, and damaged the engine mount. A second Tiger was similarly defeated from a frontal aspect at 1,100 meters. Word spread quickly through the Allied tank forces. The supposedly invincible Tigers could be penetrated from the front. Morale improved dramatically. Tactical doctrine began to change. Tank crews no longer needed to take extreme risks attempting flank shots. They could engage from prepared positions at longer ranges. The psychological impact was as significant as the technical one. German tank crews who had enjoyed a sense of near immunity in their heavy tanks found themselves suddenly vulnerable. On the German side, the change was noticed immediately, but its cause remained mysterious for months. Hauptmann Friedrich Schulz, a Tiger Company commander with Panzer Division Hermann Göring, recorded in his unit diary that beginning in late April 1943, American anti-tank weapons suddenly became much more effective. Where previously his tanks had shrugged off frontal hits, they were now sustaining penetrating damage from weapons that should not have been capable of such performance. Schulz ordered inspections of damaged tanks and was puzzled by what his maintenance officers reported. The penetration holes were different, cleaner with less spalling and fragmentation around the impact point. The shells themselves, when recovered from disabled tanks, showed less damage than expected. They appeared to have remained intact through the penetration, rather than fragmenting. German metallurgists eventually obtained samples of the new Allied ammunition and conducted their own analysis. Dr. Wilhelm Krupp, working for the Army Weapons Office, was the first to understand what the Allies had done. His report, dated July 1943, noted with grudging admiration that the American shells featured a sophisticated hardness gradient that optimized penetration against face-hardened armor. He recommended immediate development of countermeasures, either thicker armor or modified face-hardening processes that would defeat the gradient principle. But by this point in the conflict, German industrial capacity was already strained. Increasing armor thickness would require heavier tanks, larger engines, more fuel consumption, and more manufacturing resources. They simply could not respond quickly enough. The impact of Frost's innovation extended beyond anti-tank weapons. By late 1943, the process was being applied to naval armor-piercing shells, aircraft cannon ammunition, and even to the armor plate of Allied tanks. The principles Frost had discovered about controlled hardness gradients opened new areas of metallurgical research. Engineers began to understand that optimal material properties were not about maximizing a single characteristic like hardness, but about creating property gradients tailored to specific applications. Frost himself continued working at Aberdeen throughout the conflict, developing refinements to his process and applying the gradient principle to other problems. He was awarded the Presidential Medal for Merit in November 1944, though the citation could not specify his exact contribution due to security classification. His colleagues, including Dr. Holbrook, who had initially dismissed his ideas, came to regard him as one of the foremost applied metallurgists in the country. After the conflict ended, Frost returned to academic research, but his reputation had been transformed. He published a groundbreaking paper in 1947 titled Microstructural Engineering Through Controlled Property Gradients that became foundational to modern materials science. The statistical impact of the Frost process is difficult to quantify precisely, as improved ammunition was introduced alongside other tactical and technological developments. However, analysis of combat records suggests some striking patterns. American tank destroyer units using 3-inch guns recorded a 320% increase in Tiger penetrations between March and June 1943. British units equipped with 17-pounder guns firing Frost process ammunition reported similar improvements. German tank loss rates to frontal hits increased from approximately 12% before April 1943 to 41% by September of that year. Perhaps more significantly, the development changed how both sides thought about the relationship between offense and defense in armored conflict. The Tiger tank had represented a philosophy. Build armor so thick and hard that nothing could penetrate it. This approach had a certain elegant simplicity and had proven highly effective early in the conflict, but it also made German tanks progressively heavier, slower, more fuel-hungry, and more expensive to produce. A single Tiger required 300,000 man-hours to manufacture and consumed enough steel to build 3 medium tanks. The Frost process represented a different philosophy. Understand your enemy's strength at a deep level, then engineer a specific solution that exploits the hidden weaknesses within that strength. It was an approach that required scientific sophistication, precision manufacturing, and systematic testing. It could not rely on brute force or simple scaling. This philosophy aligned well with Allied industrial and scientific advantages. Where German production emphasized building smaller numbers of individually superior weapons, Allied production emphasized building larger numbers of sophisticated but mass-producible weapons, optimized for specific tasks. The human element of this story reveals itself most clearly in the correspondence between Frost and the tank crews who used his ammunition. After the conflict ended, Frost received hundreds of letters from soldiers who wanted to thank the anonymous engineers who had given them a fighting chance against German heavy tanks. Many described the psychological transformation that came with the new ammunition. Before, encountering a Tiger had meant probable defeat and possible loss of life. After, it became a challenge that could be met with skill and proper tactics. One letter from former Sergeant Mitchell described the moment of his first successful frontal penetration in detail. He had been terrified, he wrote, expecting his shot to bounce off harmlessly and draw return fire that his thin-skinned tank destroyer could not withstand. When he saw the shell punch through and the Tiger stop, he experienced what he described as a complete reversal of psychological momentum. The monster had been tamed. He and his crew went from feeling hunted to feeling capable. That psychological shift, he believed, was as important as the technical one. German tankers experienced the inverse transformation. Hauptmann Schultz's diary entries from mid-1943 show a progression from confidence to anxiety, to fatalistic determination. Early entries describe the superiority of the Tiger and the inadequacy of Allied anti-tank weapons. Later entries note the changing effectiveness of enemy fire with concern. By August 1943, Schultz writes matter-of-factly about frontal armor no longer providing reliable protection and discusses tactics for maximizing survivability despite this vulnerability. The psychological armor provided by thick steel had been stripped away, and with it went some of the aggressive confidence that had characterized German armor tactics earlier in the conflict. The story also illustrates how innovation often comes from unexpected sources and challenges established hierarchies. Frost was not a senior figure in the metallurgical community. His academic work had been respected but not celebrated. He had no experience in ammunition design before 1942, yet he solved a problem that had stumped more experienced specialists precisely because he approached it from a different angle. He was willing to question assumptions that others took as axiomatic. He understood that harder is better was not a universal truth, but a context-dependent guideline. His theoretical background in grain boundary mechanics gave him insight into failure modes that practical engineers had not considered. Colonel Webb, to his credit, recognized that conventional approaches were failing and gave Frost the opportunity to test an unconventional idea. Despite significant skepticism from experts, this willingness to experiment, even with limited resources and under time pressure, reflected a pragmatic flexibility that proved essential to Allied success in many technical domains. The Germans, despite their considerable scientific and engineering expertise, were often more rigid in their approaches, more committed to established doctrine, less willing to risk resources on unproven concepts. This cultural difference in innovation style became increasingly important as the conflict progressed. The production challenges surrounding the Frost process also reveal important aspects of American industrial capability. Converting from conventional to gradient heat treatment required new equipment, new training protocols, new quality control procedures, and acceptance of lower initial production rates during the transition. In mid-1943, with ammunition demand at extraordinary levels and frontline units constantly requesting more supplies, this conversion represented a significant gamble. If the new process had not delivered the promised improvements, the production disruption would have been costly. But American industry managed the transition successfully, demonstrating the flexibility and technical sophistication that characterized its approach to conflict production. By the time the conflict ended in Europe in May 1945, the Frost process had been refined through multiple iterations and applied to dozens of different ammunition types. Post-conflict analysis by the U.S. Army's Ordnance Department concluded that the innovation had increased the effective penetration capability of American anti-tank weapons by between 35 and 55%, depending on specific weapon and target combinations. This translated to thousands of enemy tanks defeated that might otherwise have survived, and thousands of Allied soldiers who survived engagements they might otherwise have lost. Frost lived until 1983, long enough to see his work recognized as pioneering in the field of functionally graded materials. The principle he discovered, that optimal material properties often involve gradients rather than uniformity, became central to advanced materials engineering. Modern applications range from dental implants with graded hardness to aerospace components with graded thermal properties to armor systems far more sophisticated than anything conceived during World War II. Every time an engineer designs a material with intentionally varied properties across its structure, they are applying the insight Frost developed while trying to defeat Tiger armor in that cold Maryland workshop. The broader lesson of this story extends beyond metallurgy or military history. It speaks to how progress often emerges from the willingness to question what seems obvious, to look at familiar problems from unfamiliar angles, to persist despite skepticism from established authorities. Frost's stupid heat treatment trick succeeded because it challenged a fundamental assumption that armor-piercing projectiles should be uniformly hard. Once that assumption was questioned, new possibilities opened. The obvious solution, make shells harder, had reached its limit. The non-obvious solution, make shells strategically softer in certain areas, proved transformative. This pattern appears repeatedly in the history of innovation. Breakthroughs come not from doing the accepted thing better, but from questioning whether the accepted thing is actually optimal. They come from people willing to look foolish, to propose ideas that colleagues dismiss, to invest enormous effort in testing concepts that might fail. They come from organizations willing to support such people, at least occasionally, even when the odds seem long. Harold Frost could easily have remained a comfortable but obscure academic. Instead, driven by necessity and opportunity, he became an innovator whose work influenced the course of history and the development of materials science for generations after. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II and check out the video on screen for another incredible tale from history. Until next time.